Hello again, welcome to the continuation of our lecture 4, and this is part 2 of the lecture video. Today, we will elaborate the nuclear energy. The best known fission reaction involves the split of the uranium atom, the U-235 isotope, into another elements and is commonly used to generate electricity in nuclear power plants. Actually, 443 of them in 2006 generated 370,000 megawatts worldwide to power nuclear submarines, aircraft carriers, and even to power spacecraft. The first nuclear chain reaction was achieved by Enrico Fermi in 1942, and the first large-scale nuclear reactors were built in 1944 for the purpose of producing material for nuclear weapons. When a uranium-235 atom absorbs a neutron and split during a fission process, it produces 2 lighter nuclei and 3 neutrons. In this case, it produces a cesium-140 atom, a rubidium-93 atom, and 3 neutrons, which has 3.2 times 10 to the 11 joules of energy. In practical terms, the complete fission of 1 kilogram of uranium-235 releases 6.73 times 10 to the 10 kilojoule of heat, which is more than the heat released when 3,000 tons of coal are burned. Therefore, for the same amount of fuel, a nuclear fission reaction releases several million times more energy than a chemical reaction. While in nuclear energy by fusion, it is released when 2 small nuclei combine into a larger one. The huge amount of energy radiated by the Sun and the other stars is thought to originate from such a fusion process that involves the combination of 2 hydrogen atoms into a helium atom. When 2 heavy hydrogen, in this case deuterium, nuclei combine during a fusion process, they produce a helium-3 atom, a free neutron, and 5.1 times 10 to the 13 joules of energy. Fusion reactions are much more difficult to achieve in practice because of the strong repulsion between the positively charged nuclei, called the Coulomb repulsion. To overcome this repulsive force and to enable the 2 nuclei to fuse together, the energy level of the nuclei must be raised by heating them to about 100 million degrees Celsius. But such high temperatures are found only in the stars or in exploding atomic bombs. In fact, the uncontrolled fission reaction in a hydrogen bomb is initiated by a small atomic bomb. Let's have a sample problem for a car powered by nuclear fuel. An average car consumes about 5 liters of gasoline a day, and the capacity of the fuel tank of a car is about 50 liters. Therefore, the car needs to be refueled once every 10 days. Also, the density of gasoline ranges from 0.68 to 0.78 kilograms per liter, and its lower heating value is about 44,000 kilojoule per kilogram. Suppose all the problems associated with the radioactivity and waste disposal of nuclear fuels are resolved, and a car is to be powered by U-235. If a new car comes equipped with 0.1 kilogram of the nuclear fuel, U-235, determine if this car will ever need refueling under average driving conditions. So, for the given, the consumption, this is the volume rate, and this is equal to 5 liters per day. For the capacity of the fuel tank, it has 50 liters, and the density of the gasoline ranges from 0.68 to 0.78 kilograms per liter, and since this is an incombustible substance, so we can take the 0.75 kilograms per liter as the average density of the gasoline. And the heating value is 44,000 kilojoule per kilogram, and the complete fission of 0.1 kilogram of uranium-235 releases a 6.73 times 10 to the 10 heat. The mass of gasoline used per day by the car is given by this expression. This is the mass flow rate, and that gasoline is equal to the density times the volume rate of the gasoline. And since the density, the average density of the gasoline is 0.75 kilograms per liter, and the volume rate or the consumption of the car is 5 liters per day, so since we need to cancel this one, liter, this is in the denominator and this one is in the numerator. So, calculating this one, 0.75 times 5, this is equal to 3.75 kilograms per day. And this is the mass of the gasoline used per day. For the energy, energy flow rate, so note that the heating value is 44,000 kilojoule per kilogram, and the energy supplied to the car per day is given by this. This is the energy flow rate, and this is equal to the mass flow rate of the gasoline times the heating value. So we have the value 3.75 from the previous calculation. 3.75 kilogram per day times the 44,000 kilojoule per kilogram, and this is equal to 165,000 kilojoules per day. And the complete fission of 0.1 kilogram of uranium-235 releases a heat. This is 6.75 times 10 to the 10 kilojoule per kilogram times 0.1 kilogram from the complete fission of the uranium-235, and this is equal to 6.75 times 10 to the 9 kilojoule of heat. And this heat is sufficient to meet the energy needs of the car for a known number of days. To determine the number of days that is sufficient to meet the energy needs of the car, so the number of days is equal to the energy content of fuel over daily energy used. And since we calculated earlier the energy content of fuel, and we've got 6.73 times 10 to the 9 kilojoule, and the energy flow rate, that is the daily energy use, we have the 165,000 kilojoule per day. Cancel the kilojoules. So we have 40,790 days, and this is approximately 112 years. Considering that no car will last more than 100 years, this car will never need refueling. It appears that nuclear fuel of the size of a cherry is sufficient to power a car during its lifetime. Now let's discuss the mechanical energy, the form of energy that can be converted to mechanical work completely and directly by an ideal mechanical device such as an ideal turbine. Many engineering systems are designed to transport a fluid from one location to another at a specified flow rate, velocity, and elevation difference. And this system may generate mechanical work in a turbine, or it may consume mechanical work in a pump or fan during this process. The kinetic and potential energies are the familiar forms of mechanical energy. Thermal energy is not mechanical energy, since it cannot be converted to work directly and completely as stated from the second law of thermodynamics. When a pump transfers mechanical energy to a fluid by raising its pressure, and remember the pressure from what we have learned from fluids, the pressure increases with depth. Okay, so this is the stronger pressure and this is the weakest pressure. And a turbine extracts mechanical energy from a fluid by dropping its pressure. Therefore, the pressure of a flowing fluid is also associated with its mechanical energy. Note that pressure itself is not a form of energy, but a pressure force acting on a fluid through a distance produces work, and it is called flow work in the amount of the pressure over the density. per unit mass. Flow work is expressed in terms of fluid properties, and it is convenient to view it as a part of the energy of a flowing fluid and call it flow energy. The mechanical energy of a flowing fluid can be expressed on a unit mass basis, as expressed this one from this equation. The energy per unit mass is equal to the pressure over density plus the kinetic energy, V squared over 2, plus the potential energy, plus Gz. Again, this is the energy per unit mass. Where this one is the flow energy, the pressure over rho. This one is the kinetic energy, and this one is the potential energy. Now, in the rate form, the energy is given by m dot times the energy per unit mass. M dot here is the mass flow rate of the fluid, and this is given by this equation, m dot times this expression. Then, the mechanical energy change of a fluid during incompressible, meaning when your density rho is constant, becomes this one, meaning the change of the energy per unit mass is given by this. So the change of pressure over rho plus change of velocity over 2 plus g times the change of elevation. And the unit is kilojoule per kilogram. And for the change of the rate form of the energy, this is given by this. Again, you just have to multiply it by the mass flow rate. And this is given by this. And the unit is in kilowatts. Therefore, the mechanical energy of a fluid does not change during flow if its pressure, density, velocity, and elevation remains constant. In the absence of any losses, the mechanical energy change represents the mechanical work supplied to the fluid. If the change of your energy per unit mass is greater than 0, or extracted from the fluid if your change in energy per unit mass is less than 0. Let's tackle another sample problem about wind energy. A site evaluated for a wind farm is observed to have steady winds at a speed of 8.5 meter per second. Determine the wind energy A per unit mass, B for a mass of 10 kilograms, and C per second for a flow rate of 1,154 kilograms per second for air. And since the only form that can be captured by the wind turbine is the kinetic energy, so for A, the wind energy per unit mass is given by the kinetic energy, and this is equal to 1/2 v squared. So velocity is 8.5 meter per second, and to convert this into joule per kilogram, so cancel, since 1 joule per kilogram is equal to 1 meter squared per second squared, so we need to cancel this one, and this is equal to 36.1 joule per kilogram. For B, the wind energy for an air mass of 10 kilograms is given by energy is equal to mass times the energy per unit mass. So 10 kilograms. So this is the condition, 10 kilograms times the 36.1 joule per kilogram. This is the value that we've calculated from here. So the energy for an air mass of 10 kilograms is equal to 361 joules. So cancel this one, kilogram and kilogram. So we have the joule. For letter C, the wind power for a mass flow rate of 1,154 kilogram per second. So the formula is the E dot is equal to M dot times E. So again, this is the energy flow rate, the mass flow rate, and the energy per unit mass. So we have the mass flow rate to be 1,154 kilogram per second, and our energy is 36.1 joule per kilogram. And if we need to convert this into watts, so in 1 kilowatt, we have 1,000 joule per second. So cancel the seconds here, seconds, the joule, and the kilogram. So we have 41.7 kilowatt. Energy can cross the boundary of a closed system in two distinct forms, the heat and work. Now, let's discuss about energy transfer. Specifically, we will discuss the energy transfer by heat. Heat is defined as the form of energy that is transferred between two systems or a system and its surroundings by virtue of a temperature difference. So, say for instance, in this figure, here, there is no interaction between the system and the surroundings. Therefore, there is no temperature difference, so there is no energy transfer. But here in this case, since we have a temperature difference, so eventually there is a energy transfer by heat. Okay? So in short, temperature difference is the driving force for heat transfer. The larger the temperature difference, the higher is the rate of heat transfer. Heat is energy in transition. It is recognized only as it crosses the boundary of a system. Consider this hot-baked potato, okay, in this figure. The potato contains energy, but this energy is heat transfer only as it passes through the skin of the potato. The skin of the potato here is the system boundary to reach the air, the surrounding air. Once in the surroundings, the transferred heat becomes part of the internal energy of the surroundings. Thus, in thermodynamics, the term heat simply means heat transfer. Now, let's discuss about adiabatic process. This is a process during which there is no heat transfer. Say for instance, at this figure, this is a typical example of an adiabatic system. And as you can see, there is an insulation around it or across its boundary so that there is no heat transfer. And the word adiabatic comes from the Greek word adiabatos, which means not to be passed. And there are two ways a process can be adiabatic. Either the system is well insulated so that only a negligible amount of heat can pass through the boundary, or both the system and the surroundings are at the same temperature, and therefore there is no driving force. There is no temperature difference for heat transfer. An adiabatic process should not be confused with an isothermal process. Even though there is no heat transfer during an adiabatic process, the energy content and thus the temperature of a system can still be changed by other means such as work. And as a form of energy, heat has energy units, kilojoule. And the amount of heat transferred during the process between two states, for instance, between states 1 and 2, is denoted by Q, big Q, Q12, or just big Q. Okay? So the heat transfer per unit mass of a system is denoted by this equation. So here, this is the heat transfer between two states. So we denote this by this variable Q, and here is the mass. So this is the heat transfer per unit mass. And to know the rate of a heat transfer, meaning the amount of heat transferred per unit time, instead of the total heat transferred over some time interval, the heat transfer Q here, the rate of the heat transfer has a unit of kilojoule per second, okay, or just kilowatts. This is kilowatts. And here, The heat transfer rate Q varies with time, meaning the amount of heat transferred during a process is determined by integrating Q here over the time interval of the process. And if Q remains constant during a process, it can be reduced into this equation. Here, this is the Q and this is the rate. Delta T here is the time interval during which the process takes place. Again, its unit is in kilowatts. How about when energy is transferred by work? Work, like heat, is an energy interaction between a system and its surroundings. And heat is easy to recognize. When there is temperature difference between the system and its surroundings, meaning there is heat. So, if the energy interaction that is not caused by a temperature difference between a system and its surroundings, then we can say that the energy transfer is by work. So, work is the energy transfer associated with a force acting through a distance. And work is also a form of energy that is transferred like heat, and therefore it has units of kilojoule. And when the work done during a process between states 1 and 2 is denoted by work subscript 1, 2, or just work, capital W. Okay, and the work done per unit mass is denoted by this small w and is expressed as this equation. So it has units of kilojoule per kilogram. And the work done per unit time is called power and denoted by work dot, this one, big W dot, and it has units of kilowatts. So heat and work are directional quantities, and thus the complete description of a heat or work interaction requires the specification of both the magnitude and direction. So one way of doing that is to adopt a sign convention. So take a look at this figure. So when the heat transfer, this one, heat transfer to a system. So meaning heat is going into the system, and also when work is done by a system, this one, so these are positive. And if the heat transfer from a system, meaning it goes out, and the work done on a system, so it has a sign of negative. So again, we can, another way is to use the subscripts in and out to indicate direction. So in is positive, out is negative. We need to stop here, and I will continue the topic to the next lecture video. I will see you soon. Thank you for listening.